Hi. Today I wanted to make sort of tutorial just to show some examples of the problems. They partly coincide with what you had in the assignments, partly are small variations of them. So consider the problem number 1. Equation it's a string equation on the segment between 0 and 1, f between 0 and 1. Initial conditions u for t equals 0 equals x, ut for t equals 0 equals 0. And the boundary conditions, say we take the Differential conditions, u for x equals 0 equals 0, u for x equals 1 equals 0. So this is our problem. So because we have here the Differential conditions and the function is 0 at x equals 0 and x equals 1, we can continue the initial conditions as odd functions reflected over all the endpoints 0 and 1, and then over reflected points, and so on. I shall show you, and then solve this equation as if it was equation in the half space for x half plane t more than 0, x is from minus to plus infinity. So let's draw a picture. It is 1. So this is the graph of the initial condition u of x1, x0 equals x. Now let us continue it as odd function from 0 to minus 1. Yes, so if it is x here, then if we continue, it is x here. So this way we continue it here. Now we have to continue it as odd function relative to the point 1. So this is 2, this is 3. So it is, here we have discontinuity. And again, we have this situation. So this way we defined this function, continuation of our function, on for x between 1 and 3. Similarly, we continue it for x between minus 1 and minus 3. So it is minus 2, it is minus 3. So it is like this. Yeah. This is 1, this is minus 1. And so on. And we have this function which is linear between minus 1 and 1, between 1 and 3, between 3 and 5, and all. It's periodic function, and we denote this function as a function phi of x. So phi of x is a continuation of function f of x. F of x is initial condition for u for t equals 0. It is a continuation to all of the line. It is one thing. And now you solve the following problem. V tt minus v xx equals 0. Now on the whole line x between minus and plus infinity, u v for t equals 0 equals phi of x, vt for t equals 0 equals 0. Yeah? So if v is solution of this problem, then if you take this v between minus 1 and 1, between 0 and 1, value between x between 0 and 1, we have the desired function u, a solution of this problem, because it will automatically have the 0 value at the point 0 and 1. So here this second condition means that solution has the following formula: v of xt equals 1/2 phi of x plus t plus phi of x minus t. So this is solution of this problem. And uxt equals v of xt if you consider x between 0 and 1. So just restrict this function v on, for x between 0 and 1. So this gives us the full solution, but the thing is that we have to find it. It is this formula, but now we have to find what is phi of x minus t, phi of x plus t, what is the formula for them. No, we start from the function phi itself. So phi x, let's write what it is. So between minus 1 and 1, this function equals x. X it is x if x between minus 1 and 1. Here it is a linear function. Here it is x minus 2 if 1 less than x. One moment, I would not write here equality because the endpoints are the points of discontinuity. Less than 3. The next is here. It is the point 4. Yeah. So it is x minus 4 if 3 less than x less than 5, and so on. It is x minus 2n if 2n minus 1 less than x less than 2n plus 1. And here n can be positive and negative. So, for example, this piece, it is minus 2, it is x plus 2 if minus 3 less than x less than minus 1. X plus 4 if minus 5 less than x less than minus 3, and so on. So we defined this function piece by piece. So It is the first component of solution. Now let us draw the picture in the xt plane. It is x-axis, it is t-axis. And our initial conditions are given for t equal 0. It is 1, it is minus 1. 2, 3, 4, 5, and so on. Minus 2, minus 3, minus 4, minus 5, and so on. Now, the function is a linear function, just phi of x equals x on the segment from minus 1 to 1. Yes? So if, now let us draw the characteristics from going from the point minus 1 and 1, from minus 1 goes to the right, from 1 goes to the left, and if we take a point here, xt, then x minus t and x plus t are between minus 1 and 1. Yes? So this means that here we can use this formula for phi of x, for this piece of the function. Yes? And this means that in this domain, which let me denote it by, say, let me denote by d1, but let me write it domain number 1. I have to write here. Yes, let me keep this formula, and I will apply this formula piece by piece. So u of xt equals the following. In domain number 1, it is 1/2 x plus t plus x minus t in domain number 1. Domain number 1 is what I depicted here. Now we consider the next domains. One moment. No, it is wrong. So it is 1, it is 3. I have to draw characteristics through all the points where the this function phi of x is discontinuous, or its derivative is continuous. These points are called singular points. So this function phi of x was like this. It is point 1, it is point 3, it is point 5, and so on. Minus 1, minus 3, and so on. So we have the points where the function is discontinuous. And this means that if we say change it from this domain number 1 to the next domain, which is, I will denote it domain number 2 in a short time, then the point x plus t gets here in the segment between 1 and 3. And here between 1 and 3 we cannot write phi of x as x, it is x minus 2. Yes? So I will proceed this way. So if you draw the characteristics, next characteristics, minus 1, 3, minus 1, minus 3, like this. Yes. Then we have here domain number 2. In domain number 2, if xt is in domain number 2, then x plus t is between 1 and 3, and x minus t is between minus 1 and 1. Correspondingly, in this term, in this form of phi of x plus t, I have to substitute here. It is x plus t minus 2. And phi of x minus t is x minus t again. So it is 1/2 phi of x plus t, it is x plus t minus 2 plus x minus t, which is equal to x to x, t is cancelled, minus 2, so x minus 1. In D2. And this is equal x. In D1. Now consider domain number 3. It is this domain, number 3. In this domain, the function, if I take the point xt here, then x plus t is between minus 1, between 1 and 3, and x minus t is between minus 1 and minus 3. So I have to use this formula for phi of x plus t, and this formula for phi of x minus t. So let me write it. 1/2 x plus t minus 2 plus here phi of x minus t, it is x minus t minus 2, which is equal to x to x plus t minus t plus 2. Plus 2. Yes, so 2 is cancelled, t is cancelled, it remained x in D3. No, okay, let me draw again this characteristic and this characteristic to the point minus 5, and we have new domains. Now we are interested in domain number 4. In domain number 4, x plus t is between 3 and 5, and x minus t between minus 3 and minus 1. So this means that it is equal 1/2 x plus t between 3 and 5 minus 4. Minus 4 plus x minus t plus plus 2 equals x minus 1, because we have to multiply by 1/2. It is x minus 1 in D4. So, oh my God, what we see? We see here it is x, here in D2 it is x minus 1. In D3 it is x minus 1 here, Okay, our solution U, no, the pattern is clear. It is X in domain D, if I numerate them, domain D5, D6, and so on. It is X in domains with odd number and X minus 1 in domains with even number. But now I would like to say that we are interested in solution when x is between 0 and 1, only the function in this strip, which is here. And in this strip we have just pieces from domain number 1, 2, 3, 4, 5, and no other. Yes? So let me draw it in a larger scale. This way. Then this way. So it is t, it is 1, so t is 1, so t is 2, 3, and so on. So it's domain number 1, domain number 2. So you, and now they know that here u is x, no, u is ux1 and 2. Here u equals x minus 1. Here u is x, u equals x minus 1, and so on. And next I ask you usually to draw the picture of solution, solution V of xt. So it is vibration of string. Yes? So at every point, at every time moment, we see some shape of string. So just to draw the shape of the string at different moments. So to say, create a movie. Let's create a movie here. So what is the shape of string at the time 0? At the time 0, it is from here to here, for t equals 0, it is just u of x0 is x. So I draw the graph of this function. This is, it is for t equals 0. Now, what else? Let us take t equals 1/4. It is 1/4. At t equals 1/4, we take this horizontal segment. So 3/4 is in the domain 1. So for 3/4 of its length, the string has the shape of the function y equals x. Yes? And here, starting from the point 3/4, it has the shape y equals x minus 1. So it is here, like this. No, like this. So this is the shape of the string at t equals 1/4. At t equals 1/2, it is here. At t equals 1/2. This new discontinuity will be at the point in the midpoint, yes? Because half of this length, this segment is in domain number 1, and the other half in domain number 2. So it is like this, and then like this. Yeah? So we see that this discontinuity travels along the string. Yes? At t equal 3/4, I can draw it. T equal 3/4. It is here. Yeah? T equal 3/4. So it's the point 1/4. And at t equal 1, for t equal 1, we are this segment is completely in the domain number 2. So here u equals x minus 1. So it is here, like this. Yeah? T equals 1. So what goes next? Next we are here. So if you take the moment just a minute, 1.5. So it is 3 seconds. Here this segment, half of it in the domain where u equal x, and half in the domain where u is equal x minus 1. Yes? Okay, let us take for clarity here, it is 5/4. It is 1 and 1/4, yeah? In this segment. So 1/4 is in the domain number 3, where u equals x. Let me draw it here. There's 1/4. And 3/4 in the domain u equal x minus 1. So we are going along this segment. It is t equals 5/4. T equals 3 seconds. It is this segment, so half of this where u equal x, and half where u equal x minus 1. If you take t equals 1 3/4, it is how much? It is 7/4. Then 3/4 it is where y equals u equals x, and 1/4 where u equals x minus 1. So you see how it looks. This discontinuity travels along the segment. Yes, it reaches the left end, and then reflects back. Yeah, you see how it looks. And then at the moment t equal 2, we have u equals x. It is t equals 7/4, and at t equal 2, again we have this one. T equal 2. U of x t when t equal 2 equals x. Yeah? So we return to initial situation. And no wonder that if you continue it further in time, it will all repeat periodically. So we go this way and then again this way and so on. So we have here some number of frames of this movie, and then this movie will run periodically. Now this periodicity is, I would say, characteristic for the string equation on finite segment. That's it. So we can go further and consider other problem. Similar problem for this equation. other problem. Again, utt minus uxx equal 0. X between 0 and 1 again. U t equals 0 equal x. Ut for t equals 0 equals 0. So the initial conditions are the same, but the boundary conditions are a little different. U for x equals 0 equals 0, and ux for x equal 1 equals 0. So the difference is in this boundary condition. In this boundary condition. Okay, so we have to again work with reflections. So our function f, which is this function x, this function f is defined between 0 and 1. And between 0 and 1, f of x equals f of x. F of x equals x. Now the left end is fixed of the string. This means that here we have to reflect it in odd manner. So the function x from 0 to 1 is continued as x between 0 and minus 1. But the right end is the free end. It can move freely. This means that here we have to use the even continuation. This continuation. We take this piece and reflect it in the point 1, so here is point 2, this is a point 3. Yes? Now we continue, this is again the point which is reflection of this point, so we have to continue this in the as an even function relative to 3 farther. It is 4, it is 5, and so on. And similarly here, from here we continue it like this, minus 2, minus 3. From here we continue like this. Yes, minus 4, it is minus 5, and so on. So we have a different function, so this is a function phi of x. And now we solve the problem v tt minus v xx equals 0, and this time x between minus infinity and plus infinity on the whole line. V at t equals 0 equals phi of x, this function, so vt for t equals 0 equals 0. No, in this case. Otherwise we had to continue the second function. This is g of x. But if it is 0, we don't need it. And again, I repeat it all. Our solution v of xt equals 1/2 phi of x plus t plus phi of x minus t. Yes? And if you find this function v, then we can write that u of xt equals v of xt if you take x between 0 and 1. Yeah, so it is a restriction of the function v on the strip x between 0 and 1 and t all positive coordinates. Okay, so to this end we have to describe the function phi separately on each segment, and then use a similar partition of our the plane xt into domains and find the function v by this formula in each of these domains, where it can be described by some analytical formula, no, and then extract I would say implications from this. So let us describe this function phi. So phi of x. So when x is between -1 and 1, the function is x if x between -1 and 1. It's here. Now, when it is between 1 and 3, it is, I would say, 2 minus x. Yes? 2 minus x. X between 1 and 3. If x between 3 and 5, it is x minus 4, because it's 0 here. X minus 4. 3 less than x less than 5. No, okay, so it is 6 minus x if x between 5 and 7, and so on. And in the negative side, it is here x between -1 and 1, and between -3 and -1 it is -2 minus x. X between -3 and -1. Yes? Later it will be x plus 4. Between -5 and -3. -6 minus x. If -7 less than x less than -5, and so on. No, I think what we have already is enough to describe this function. Now we have to find partition of our plane xt in the domain, so that in each domain we can use one of these expressions for both phi of x plus t and phi of x minus t. So so the singular points where the function is not smooth, so here the function is not smooth at the point 1, 3, 5, -1, -3, and so on, in all odd integer values. So let us mark these points. It is 1, 2, 3, 5, no, 7, minus 1, minus 3, minus 5. No, I hope it's enough. Now, let us draw the characteristics through the points 1 and minus 1. In this triangle, which I denote by domain number 1, we have that if x plus t and x minus t are, if the point xt is in this triangle, then x plus t and x minus t are between minus 1 and 1. So both we can use this formula. So at domain number 1. Now we have further domain, no, it's too high. So domain number 1, we need domain number 2, domain number 3, 4, and domain number 5. No, if necessary, domain number 6. Why I consider only these domains? Because we need only this strip between x, between 0 and 1. So this strip, it has intersection only with these domains. And now I have this description of the function in different segments here, between minus 1 and 1, 1 and 3, 3 and 5, and so on. So I will use it to describe, to find the expression of the function u in every one of these domains. So, u of xt equals, in domain number 1, it is 1/2 x plus t. I have to use, so phi of, just a minute, u of xt, v of xt equals 1/2 phi of x plus t plus phi of x minus t. Yeah, so here in domain number 1, both x plus t and x minus t are here. So we have simply here x plus t plus x minus t, which is equal to x in domain number 1. In domain number 2, x plus t is between 1 and 3. Between 1 and 3 is 2 minus x. So it is 1/2 2 minus x plus t. And if you x minus t is between minus 1 and 1, so we use this plus x minus t, which is equal to 1. Here is minus x, here is plus x, so x cancels out, 2 minus t, and here minus t. So 2 minus 2t times 1/2, it is 1 minus t in D2. In domain D3, we have both x minus t between minus 3 and minus 1, and x plus t between 1 and 3. So it is 1/2. So for x plus t we use this 2 minus x plus t, and for x minus t it is here between -3 and -1, -2 minus x minus t. Yeah. What is this? 2 and -2 cancels, minus x and minus x, so minus 2x, so it is minus t here plus t, so it is simply minus x in D3. Now in D4, x plus t between 3 and 5. Between 3 and 5 it is x minus 4. So 1/2 x plus t minus 4. And here it is minus 2 minus x minus t. X minus t, which is equal okay, x plus t, so x minus x, one moment, x minus x, t plus t, so it is 2t minus 6 divided by 2, it is t minus 3 in D4. No, okay, let it be. In D5, x minus t is between -5 and -3, and x plus t between 3 and 5. So it is 1/2. Here, so here between 3 and 5, it is x plus t minus 4. Between -3 and -5, it is plus x minus t plus 4. Yes, we have this formula. So 4 cancels, t cancels, it is x in D5. Okay, so we return to the initial. So it is x here, and it is x here. So starting from this, everything repeats periodically. So this is t equal 1, 2, 3, 4. This means that the period of this solution now is 4 with this boundary condition. Now what remains is to draw the movie. So let me do it. So solution is here. So I need some space to draw the movie. Wait, what I'm doing. So let me repeat it here in larger scale. So it is 1, it is D1, it is D1, D2, D3, D4. D2, D3, it is D4. So here in D1, our function u equals x. Here u equals 1 minus t. Here u equals minus x. And here, just a minute. Not enough space. This is one. So it is D1, D2, D3, D4, it is D5. So here u equals x, here u equals 1 minus t, here u equals minus x, here u equals t minus 3, and here u equals x again. So it is 1, 2, 3, 4. The point 4. Okay, so for t equals 0, it is this segment. Here t equals 0, u equal x. No, let me draw it this way. T equals 0. What happens next? Let us take t equal 1/4. Then 3/4 of this segment, t equal 1/4, is in domain D1. So in the domain 3, here it is here, yeah? And then u equal 1 minus t. So if t equal 1/4, so it is 3/4. It is a constant. So it is 3/4, and this is 3/4. It is t equals 1/4. For t equals 1/2, for t equals 1/2, part of 1/2 of this segment, the function is again x, and then it is 1 minus t, so it is equal to 1/2. It is t equals 1/2. For t equals 3/4, let me here. We have the picture where it is 1/4 is here, is occupied by, is like this. Here the function is equal to x, and here it is 1/4. T equals 3/4. And for t equal 1, we are completely in domain D2. In domain D2 it is 1 minus t. For t equal 1, the solution is 0. T equal 1. Yeah. Now we go further. For t equal 1 and 1/4, 5/4. 1/4 is in D3. In D3 it is minus x. And here it is 1 minus 5/4 is minus 1/4. So it is this. Solution is this. No. It is t is 1 again. 1/4 minus 1/4. Yeah. It is t equals 5/4. For t equal to 3/2, we have similarly a solution looks like this. It is 1/2, and this is minus 1/2. Yeah, t is 3/2. Now for t equals 2, it is here. We are completely in D3. It is minus x. It is for t equal 2. No, now it is here. Now here, if you take 2.5, then here it is minus x. And here it is 2.5 minus 3, it is minus 1/2. So it is 1/2 minus 1/2. Yeah, it is t equals 5/2. It is here. For t equal 3, for t equal 3, we are completely in the domain number 5. No, domain number 4, and domain number 4 with t minus 3. For t equal 3, it is 0. It is 0. And now for t equal 3.5, 3.5 here. We have here it is u equal x. No, I'm sorry. It is 1/2, and here it is again in D4. It is t minus 3, so it is 1/2. So t is 3.5. It is 7/2. And for t equal 4, we are in D5. It is x. Again, it's t equal 4. So again, we return to the first picture. And then everything goes the same way periodically with period 4. So in the previous problem, if you can recall, period was 2, and here the period is 4. So u of x t plus 4 equals u of xt. So it is, period is 4. Now we can also consider we have two other possibilities for the same initial conditions, but we can play with again with the boundary conditions. So I can consider the problem, this one. Again, utt minus uxx is 0. X between 0 and 1. U for t equals 0 equals x. Ut for t equals 0 equals 0. Oh, I'm sorry. I'm sorry. Okay, so it is initial condition, and this time I write ux for x equals 0 equals 0, and u for x equal 1 equal 0. Take this combination. I just wanted to see again the function phi of x. So between 0 and 1, this function phi of x equals x. Now, at the point 0, we have the Neumann condition, ux for x equals 0 equals 0. This means that here we have to reflect it as even function. At the point 1, we have Dirichlet condition. So this means that relative to the point 1, we have to reflect it as an odd function. Yes? Now, point minus 1 is also Dirichlet condition, so we have to reflect here also as an odd function. And so on. So we have this strange function. So it is 1, 2, 3, 4, 5, and so on. In this case, of course, we can do the same. We can describe this function as by formulas for linear function on each of these pieces. Now each piece is between some n and n plus 1. And then consider the partition of the plane xt into corresponding domains, write corresponding expression in each of these domains, and so on. Let me spare you and myself from this task. Now you understand pretty well how to do it. If you need to do it, you will do it. If you don't need, possibly you should not. So let us finish this sort of problems, and next I consider different sort of problems. Okay, let's consider some other problem. Another problem. Utt minus uxx equals 0. No, this time it is on the half line. Between 0 and infinity. U for t equals 0 equals 0. Ut for t equals 0 equals 0. And the boundary condition this time will be different. U for x equals 0 equals some function h of t. Function of t. I think this is a different problem, and possibly you had some difficulty with solving this because it is of a different type. And to solve this problem, we cannot use any ready formula. For this problem, we have to apply some thinking. First of all, we look at this solution and see that any solution of the string equation has the form u of xt equals v of x plus t plus w of x minus t. It is the first observation. Then, what is u, v, and w? Let us look what happens for t equals 0. We have v of x0 plus w of x0 equals 0, and derivative, time derivative, v prime of vx plus wx equals 0, v prime of x minus w prime of x equals 0. Now if you differentiate this, we will find that v prime is 0, w prime is 0, and we have nothing to do but have v of x equal 0, w of x equal 0 for x positive. So nothing, for now, nothing good. But now, if you look at this formula, you see that if we take positive t and positive x, then x plus t is also positive. And for positive x plus t, v of x plus t is 0. Yeah? If it is 0, then you can neglect this. Anyway, it is 0 for positive x and positive t. We are working there. So this means that u of xt, solution of this problem, is just w of x minus t. And all we know about this function is that w of this argument is w of x minus t equal 0 for x more or equal than t, or x minus t more or equal than 0. Yes? But here, if you look at this diagram, xt plane, the function w x minus t is constant on these characteristics. Yes? And in this domain, we don't see, we still have to find this function w in this domain where the argument x minus t becomes negative. Yes? To this end, we have to continue the function w from positive x, where it was 0, to negative x. Yeah? So let us write u, we have only one thing, one way to use the last condition. U of 0 t equals w of x minus t which we don't know, but it is, by this condition, equals to h of t, which is a given function. So we can write that w of minus t is h of t, so w of t equals h of minus t if t is negative, or w of minus x is of x is h of minus x if x is negative. And so we find solution. Solution is this: u of xt equals w of x minus t equals 0 if x more or equal than t, and h of what? Of minus x minus t. Yes? So is minus x plus t. X less than t. Or h of equals 0 x more than t, h of t minus x if x less than t. Yes? So we found this solution. Now consider examples. Examples. H of t equals, say, t cube. Yes? Then we have solution, just substitute here u of xt equals 0 when x more than t, and t minus x cube x less than t. So in this diagram, this means that we have to find point t. We know here what is h here, the function h, and then we draw this characteristic for this point, x equals 0 and t, and our solution is constant along this characteristic, and it is equal to the value of this function h at this point t. Yes, so this means that we solve this equation. Very good. There is other problem which is even more, I would say, interesting. Can I use this term interesting in this context? I hope I can. So it is the following problem, no, maybe regarded as physical. Consider a semi-infinite string, yes, whose shape is given by, no, let me draw it more expressive, yes, shape is given by u, okay, it is x, this is y, y equals u of xt. So it is the string, semi-infinite string, and here we have freely moving end, so we have here, say, a ring which is sliding along this vertical rod, yes, up and down, but there is some mass which is attached to this ring, to this point, at this point where this string is connected to the y-axis. Mass m. At the initial moment, the string was horizontal, yes, and immobile. So it is defined, described by the following equation: utt minus uxx equals 0, t more than 0, x more than 0. Yes? And initial condition, u for t equals 0 equals 0, ut for t equals 0 equals 0. And let us denote the coordinate of this string, this mass on the end of the string, but h of t. Yes? And we say that correspondingly, if u is 0, for this means that h of 0 equals 0, and h prime of 0 is, say, 1. Yes? And so this means that here was a point mass, it was a horizontal strained string, and it was all at rest, and then we gave a kick to this mass, a unit kick, and it starts moving with unit speed up. So how will all this system evolve? Yes? Let us apply what we know. Suppose that h of t is known. Yes? For any h of t, we know solution. U is, let me write it again. U of xt equals 0 if x more than t, and h of t minus x if x less than t, less or equal. No, solution is continuous. So this time h is unknown function. So for any function h, this is solution. So which function should we choose? This problem does not belong completely to partial differential equations, but let me do it for completeness. So what forces are acting on this mass? We don't regard the gravity force, so we have only the inertial force and the strain of this string. This string is pulling this force in this direction, and the component, vertical component, is equal to the following thing. This force, F equals some constant, sigma, times, you see this vertical component, ux of 0t. Yes? So if derivative is negative, it pulls down. If positive, it pulls up. Yes? So, but if it slides without friction, this means that the acceleration u acceleration h, just a minute, sigma times ux. And now what in terms of the function h? Derivative of this at the point 0 equals minus sigma times h prime of t. If you substitute here x equals 0 and find derivative of this function with respect to x, you have this. Yes? So this is the force which acts on this mass. Yeah. So by the second Newton's law, it's acceleration, which acceleration, if coordinate is h of t and h prime of t is velocity, acceleration is h double prime. So h double prime of t, m, equals minus sigma h prime of t. Yes? And this equation, or h double prime of t, equals minus sigma divided by m h prime of t. So what are solutions of this equation? One solution is constant, because here we have just first and second derivatives. The solution is exponent. So h of t equals a plus b e to the power minus sigma over mt. Yes? If you remember the stuff from the ordinary equations. And initial conditions, h of 0 equals 0, h prime of 0 equals 1. Let us call it h prime of 0 is, okay, v0. Yes? Initial velocity. And so we have a plus b equal 0, and b minus b sigma divided by m equals v0. Yeah? So b equals minus v0m divided by sigma, and a equals v0m divided by sigma. And hence solution is the following. H of t equals v0m divided by sigma 1 minus e minus sigma over mt. Yes? So the graph of this function is something like this. Yeah? It has asymptote. And what is the shape of our string? The function is u of xt 0 for x more than t. So at the moment t, this is the point t. And h of t minus x. Here the function h of t. H of t minus x. It is the following. So we have to turn it from left to right, flip it this way, and start from here. So it is something like this. Yeah? And so this will propagate, this wave will propagate along the string. Yes, this point, this will be shifted, right? And h is going to some limit when t, so it will approach when t goes to infinity. This limit is v0 m divided by sigma. That's it. It's interesting problem because this is a simple, very simple model of very modern of systems which are studied in very modern science and mathematical physics. So I don't think we will reach this field in our course, but it is a very simple model of what is doing in, I would say, today's quantum field theory. So, therefore, I took some liberty to tell you this story. I wanted to tell something else in just a minute. Okay, a little more questions. There was a problem, I forgot its number, and the following. Consider the following problem on the half line. utt minus uxx is 0. X and t on the half line. And u at t equals 0 equals f of x. ut for t equals 0 equals g of x. And the boundary condition u for x is 0 equals 0. So there's a boundary condition. So the question, yes, and we have one more condition. It is given that f of x and g of x are 0 for x more than some a. So the question was, describe domain where this the solution of this problem is 0, is identically 0. No, I mean for sure, if say f and g are 0 themselves, then solution will be 0 everywhere. But I mean in general, when f and g are not 0, so where can we guarantee that solution is 0? So let us find a solution. So f and g are not 0 from 0 to a, and then they are 0. Yes? So let us solve this problem using the reflection at the point 0. It is 0. So we write phi of x equals f of x when x more than 0, minus f of minus x if x less than 0. And gamma of x equals the same, similar g of x, x more than 0, minus g of minus x if x less than 0. Yes, no, I don't put here more or equal, less equal, because maybe the function is not defined at 0, or it may be discontinuous, something like this. So let me leave it here this way. So then solution u, v of xt equals 1/2 phi of x plus t plus phi of x minus t plus 1/2 integral from x minus t to x plus t gamma of y dy. Yeah. It is solution on the whole line. This function phi and gamma are defined on the whole line. So let us look at this let us look here. Now consider this function phi and gamma. If f is 0 for x more than a, then phi is 0 for x more than a, and for x less than minus a. Yes? Because of the difference. And the same for gamma. So phi and gamma are 0 outside of this, outside of the segment minus a. Let me draw it in more detail. So it is minus a. So if x plus t is somewhere to the right of a, and x minus t also, if x plus t and x minus t are beyond this segment, then the first term is 0, because this 0 and this 0. Now, if they are on the one side of the point of this segment, so if x plus t and x minus t are both positive, so it is here, then here these are 0, and the integral from x minus t to x plus t, say this point, it is x minus t, it is x plus t, it is the point xt. Here integral over this segment is also 0, because the function phi gamma is 0. Yes? So this means that everywhere in this domain x more than t plus a, so it is x equal t plus a. So when x more than t plus a, here solution is 0. And similarly here, if x less than x equals minus t minus a. Yes? Here u is 0. So the question is maybe somewhere else it is 0. And it really can be 0 somewhere otherwise. Let us look at this function phi. This function phi is f here minus f here with a flipped function. Yes? This means that integral from minus a to a phi of x dx equals 0, simply because it's an odd function. Odd function, integral of odd function is over symmetric segment is always 0. And again, integral from minus a to a gamma of x dx is also 0. Yes? No, we don't need this. We need this. If we are somewhere here, for example, on the t-axis, then x minus a and x plus a, x minus t and x plus t are beyond this segment minus a. Yes? So for this we have to be over, let me draw this picture. If you are here, then both x minus t and x plus t are beyond the segment minus a on one hand. On the other hand, the segment from x minus t to x plus t, yeah, I don't need this, contains all this segment from minus a. Yes? And integral of gamma y over this segment from x minus t to x plus t equals integral from minus a to a, because here and here the function gamma is 0. And integral from minus a to a is 0. Yeah? So this means that here also we have u of xt equals 0. So let me show. We have this domain, we have this domain, and we have this domain. Yes? So in all this domain which I shaded, the function u is 0, solution is 0. Now we are looking at, we are solving in the right part, so we have to somehow forget about the left part. Yes? And now you have this beautiful picture. Beautiful picture showing that u is 0 for x more than t plus a. Here it is 0, and for t more than x plus a. It is this part. So, and what remains is the strip along the diagonal. So it is one such problem. Other question is what happens, what will change if here is not u but ux. If it is not u but only ux, then the continuation will be even, yeah? So plus. And this argument that integral gamma is 0 doesn't work, because gamma may be, say, positive function or non-negative, and it's because we continue it as an even function, the integral remains, integral of gamma is twice integral of g. So integral of g itself can be arbitrary. So this means that this argument does not work. Half of the argument works. I mean this part, this domain, x more t plus a. And here it may and may not be 0. It is always 0 if integral g equals 0. So u xt equals 0 here if integral 0 to a g of y dy equals 0. Then this argument works here as well. No, that's it. It was a question which I think had some, produced some difficulty. So let's finish this this tutorial, and we are going to solve other problems. This next time will be about the Laplace equation. For now, have a good time. Bye.